So in the previous power lecture, we discussed the solution for this function gk, which is obtained by setting the gradient of this function with respect to w to 0 to obtain this solution known as a Landweber iteration. So if we apply this iteratively, the update to the parameters w, then we are bound to minimize this loss function, and eventually we'll also minimize the loss function ew, which was simply norm of y minus phi times w squared, which is also one of the terms of our very original loss function, the L1 regularized least square function g of w, which is a of w plus lambda times some r of w, where r is a regularization term, is equal to norm of L1 norm of w. So if we apply this update iteratively, we are bound to minimize we are guaranteed to minimize the original loss function e of w. And also in the previous power lecture, we discussed that this is the function g of k. This is a choice that we make, and we further simplified it as this function with some constant c of k that doesn't depend on your parameter w. So now, understanding, we will now further simplify the function g of k that majorizes or upper bounds the function e of w. To develop this simplification will be very critical to understand the iterative soft thresholding algorithm, which is our goal actually. So let's simplify this function further. So we have g of k equal to beta times w transpose w minus twice of y transpose times phi plus wk transpose times beta I minus phi transpose phi times w plus the constant c k. So now we can see that this term inside the bracket doesn't depend on the parameters w. So we can write it as some constant beta times b transpose. So b is going to be the transpose of the term inside this bracket, this blue circle, divided by beta. So we can write gk further simplified as beta times w transpose w minus twice of beta times b transpose w plus some constant c of k, c subscript k. Now here in this term we can add beta times b transpose b as well as subtract beta times b transpose b. And as we know, b or b transpose doesn't depend on w. So this is just some constant. So effectively, we can simplify this function gk that we use in the majorization maximization as simply beta times w transpose w minus twice of b transpose w plus b transpose b minus, everything is constant over here now, beta times b transpose b plus c k. And now we'll just write the definition of b as well for the sake of completeness. So B is equal to 1 over beta times the transpose the term inside the bracket. So this is phi transpose y plus beta I minus phi transpose phi times w k. So this is B. We can further write it as by taking wk as separate. So this is wk plus 1 over beta times phi transpose times y minus phi times wk, which you would notice is wk plus 1. So here, if you notice, the Landweber iteration is wk, the update to parameter w to obtain wk plus 1 is simply wk plus 1 over beta times phi transpose y minus phi times wk, which is actually B, right? And we'll see why do we obtain the solution for wk plus 1 as B, because once you simplify the notation for the function g of k, it will become apparently clear. So B doesn't depend on w at all. So this is just some another constant that we can write as some constant. Again, since c of k, we can just write it as ck, but to avoid confusion, we can just write it as some constant v k, where k is to show the dependence on the iteration number, because we have wk over here, which changes after every iteration. So now finally we have very simplified functional notation for gk of w, which is this term, and this you would notice is nothing but L2 norm of, this is beta times L2 norm of B minus W squared plus some constant V k. Where B is given by this. So we effectively have g of k of w equal to beta times the norm of wk plus 1 over beta times phi transpose times y minus phi times w k minus w. I will close this now. Plus some constant v k. So this is ultimately the function that we use to upper bound our original loss function to minimize the first term in the original loss function for the L1 norm regularized least square. And you will have to remember this, this function of g of k, the definition of function g of k, because this definition of g of k would be eventually used in the later part of the lecture to derive the iterative soft thresholding algorithm. So that's it So this is all that we wanted to discuss in the Landweber iteration part of the majorization minimization algorithm. So we had in the L1 norm regularized least square J of W as E of W plus lambda times R of W, where where E of W is replaced by the function norm of Wk plus 1 over beta times phi transpose y minus phi times Wk minus W plus some constant. We can just ignore it because it doesn't depend on W, and the second term would be lambda times R of W. So now we'll see how to minimize this. We will see a very closed form solution for minimizing another function, and by combining this result and the next power lecture, we'll finally arrive at the iterative soft thresholding algorithm.